What's up, guys? Welcome back to the next video in learning mathematics. My name is Dani, and you guys watching my channel CorioWood. Okay, so we continue our truth table statements and truth. When constructing a truth table, we have to consider all possible assignments of the true and false to the component statements. When you're listing the possibilities, you should assign truth values to the component statements in a systematic way to avoid duplication or omission. The easiest approach is to use lexicographic ordering. So we have our truth table, which is P, which is we have two rows of true and false, and we have another ones in P and Q. So V8 Q. So it's true and true, true and false, false and true, false and false. The easiest one is the 2T and 2F. And we have another ones, we have P, Q and R, and notice we have 8 rows here. So the 2 row ones, if you notice, is 2 to the power of 1 is only 2 row here, and we have 4 rows. 2 to the power of 2 is 2 times 2, it becomes 4 rows. If you look in here, there is a 2 row here, and there is 4 rows here, and if you look in here, there is 8 rows here, and it's 2 to the power of 3, so it's 2 times 2 times 2. Okay, so we keep on going. If you're going 2 times 4, then you guys do the math. What's the 2 times 4? It's going to be that many tables here. So if you notice here, the two rows is 2 times 1. We have a 2 row here, and we have a 2 times 2 is 4. We have 4 rows here, and 2 times 3 is 2 times 2 is 4, 2 times 2 is 8, 4 times 2 is 8. So we have 8 rows here, and that's how it's keep on going this way. Okay, so truth table with n propositional variables will have 2 to the power of n rows. Keep in mind, doesn't matter if you're going to 2 to the power of 4 or 2 to the power of 5. You keep on going and keep on adding the rows here. So you have to keep on add the rows. If it's 2 rows, we just put 2 to the power of 1. If it's 4 rows, we put a 2 to the power of 2 and 2 times 2. And if it's 8 rows, we put a 2 to the power of 3, 2 times 2 times 2. So example, if P is true and Q is false, what is the truth values of P and Q? So we here again, we're looking here, we have if P is true and Q is false, what is the truth value of P and Q? So we've seen the P and N before. If you guys look in here, so the true and true becomes a true, true and true becomes a true, true and false becomes a false, and false and true becomes a false, and false becomes false. I think we've seen that one before. So we have a true and true becomes a true, true and false is false, and keep in mind is and, it's not or. False and true becomes a false, and false and false becomes false. Example, compute the value. Now we have the second example. We are computing the truth value of not P and P implies Q. So how are we going to compute the value of the truth value of the table of not P and P implies Q? So if you look in here, now we have a P and Q, we have a not P, and we're looking here, we're gonna put here 2T and 2F, and we're putting the TF here. So the P, if the P is true, then not P is false. If the P is true, not P is false. If the P is false, not P is true. If the P is false, then not P is true. So the P implies Q is as we said that in the previous example, if you get an A, then I'll give you reward, I'll give you money. So that's the same logic again applies here. So the true becomes a true. If you get an A, then I'll give you some money is true. If you get an A, then if I don't give you money, it becomes false because I didn't keep my promise, but you get an A. So if you didn't get an A, and if I don't have to keep my promise in these two instances here, TF, because in this one you're getting you're not getting A, so I don't have to give you money. Even if I give you, I don't give you money, it becomes a true and false. So here we have not P and P implies Q here is true. So here we have true becomes false. So false, and P implies Q is false. So here is true, false, false, and P implies Q is false. And this one becomes true because here is false. If P is false, then not P is true. True, and P implies Q is true. And here not, we have not P here. Keep in mind that this guy here becomes a true, and this guy here becomes a false. So this one is false. So now we have false, and if you're looking here is quite the opposite, it becomes a true. So true, and P implies Q is becomes a true here. Alright, so I'll remove everything from this slide. So we're going to go on the next slide. Alright, so if you guys want to read, you guys can pause this and look if it makes sense to you guys. So if you're looking here, if P is true, Q is false, then P and Q. So keep in mind that's and keep in mind it's not P. So this is the, if you look in this column here, this is quite opposite to this one. So if you look in here is true, then not P is false, and if it's false, not P becomes a true. Then we check for the P implies Q, and in this column we check here for not P and P implies Q, which is you got double F to FF and TT. Is quite opposite to this one. This guy is here. We move to the next slide. So now we're looking for the tautology. What is tautology versus contradiction? So what is tautology? Tautology is a formula which is always true. That is, it is true for every assignment of truth values to its simple components. You can think of tautology as the rule of logic. So if it's always true, it means that this is tautology in mathematics. 2 plus 2 is 4 is tautology because it's always true. The opposite of the tautology is contradiction, a formula which is always false. In other words, a contradiction is false for every assignment of truth values to its simple components. So the example show that P implies Q or Q implies P is a tautology. So how we gonna make this one? We're gonna show that one that P implies Q or Q implies P is a tautology. So how we gonna show that this one is always true? And keep in mind this is always true for tautology, and for contradiction is always false. For this guys here is always false. So now we're gonna show that we make the truth table for P implies Q, and keep in mind that's or here. Then we go to the opposite, Q implies P, and show that the formula is always true. Alright, so now we have P, which is 2 true and 2 false. We have Q, which is true false true false. P implies Q is true false true true, and we have here is Q implies P is true true false true. So we go the other way around. So here we bring our formula which says that if you get an A, then I'll give you money. So here we're going to go the same way as we explained before. So we have a T is true, then you get if you get an A, then I'll keep my promise, I'll give you money, it becomes true. If you get an A, then I'll don't keep my promise, and our implication becomes false. And so if you don't get an A, and if you don't get an A, then it doesn't matter if I keep my promise or not, it becomes a true. Then we go the other way around. The other way around is here is Q implies P is that you didn't get an F, then I'll give you money, then becomes a true. And here you got an A, then I didn't give you money, it becomes a false. And here you didn't get an A, and I didn't give you money, it becomes a true. So it doesn't matter because you if you get an A or not, so it doesn't matter if I give you money or not. So here is this is a tautology because the tautology is always true. If you look at this guys here and this guys here, P implies Q or PQ implies P is all true. So you looking here, this is tautology. It doesn't matter how you guys gonna look at this way, which angles you guys are gonna look, is gonna be always true. So this is an example of the tautology in truth tables. Alright guys, that's it for this video of the truth table. We still continue our truth tables discussion, and I'll see you guys in the next video, and bye.